In this video, we're going to prove an important and very useful theorem about the left cosets of a certain subgroup of a group. So here's the theorem. Let G be a group, and let H be a subgroup of G. We're going to show the cosets, the left cosets of H, partition G. Now you may not have seen the word partition used in set theory before, so I want to state what that means. So here's what it means to show the cosets of H, partition G. First of all, no coset is empty. Second of all, every element of G belongs to a coset. That is a left coset. And finally, if two cosets, GH and G prime H, intersect, then they're exactly the same. Okay, so let's just step back for a bit and talk about what all this is showing. In case you've never seen the idea of partitioning of a set before, here's the idea absent any group theoretic structure. So let's just say I have a set 1, 2, 3, 4, 5, not a group. Although what we're going to be partitioning in just a minute is a group. A partition of this set is some collection of subsets so that each element of the original set, let's call that S, each element of S belongs to one of the subsets and belongs in fact to exactly one of the subsets. In other words, the subsets that I break up into are disjoint from each other. They don't share any elements. So that's one example of a partition. Here's another one. So again, each element of S belongs to one of the subsets, and no two of the subsets intersect. That is, any two subsets are disjoint. Here's another one. And this is the finest partition we can get. Finest meaning the sort of the smallest particles or the smallest subsets. So those are all examples of partitions. And the most practical way to show that a collection of subsets is a partition is, first of all, show that no subset is empty. So that's the first thing we'll do. And then show that every element of the set belongs to one of the subsets. And then show that if any two of the subsets do intersect, they have to be exactly the same. In other words, if two subsets are different, then they're completely disjoint. So that's what we're going to do with cosets now. So here's the proof. So first of all, we know that no coset is empty because if G belongs to G, that is, if I take any left coset at all, this coset contains G, since the identity belongs to H, and G times that is G. Okay, so GH is non-empty. Thus, no coset is empty. No left coset is empty. By the way, I'd be remiss if I didn't mention at this point, we're talking about left cosets here. Our theorem is about left cosets, but there's nothing special about left cosets. Everything that we're going to do would be equally applicable to right cosets. It's also true that right cosets partition a group, although, as we saw in the last video, they may partition the group differently. That is, they might partition into different subsets. But we're just going to prove the partitioning for left cosets. All right, so that's part one. They were all that straightforward. This one's a little bit less straightforward, though. All right, so we want to show that every element of the group belongs to some left coset. So let's suppose that G belongs to the group. Can I find some coset, some left coset of H that contains G? And I think, well, wait a minute. What we just defined in the last video was the left coset containing G. The left coset, GH, contains G, since, again, G times the identity is G, and the identity belongs to H. All right, so each element of G belongs to a left coset. Now, usually with these partitioning proofs, if you find that parts 1 and 2 are that straightforward, what's usually going to happen is that part 3 is going to be kind of a bear. And that's going to be true here. Part 3 is going to involve a little bit more work. All right, so let's suppose that GH and G'(H) share an element. And we don't know that it's going to be G or G'. So let's call it X. And what we're going to do is we're going to show that if they share an element X, then these two cosets are in fact exactly the same set. They're exactly the same coset. Now, before I jump into doing that, I want to talk a little bit about why that is the right and sensible thing for us to be doing. Okay, because the idea that we were trying to capture over here about partitions is that different subsets that we come up with are disjoint. That is, we're splitting S or our set into completely disjoint subsets. So why does proving number 3 prove that? So what we're showing here is if two cosets share an element, then the cosets are equal. They're exactly the same set. The reason we do that is the contrapositive of this statement would be if GH and G'(H) are different sets, that is, they're not exactly the same set, then they don't intersect. That is, they're disjoint. All right, and that's really what we're trying to show. We're trying to show that different subsets in our collection are disjoint. But it's a lot easier to do something useful with the fact that these two sets have an intersection and then try to prove they're the same set than it is to assume that they're not exactly the same set and then prove that they're completely disjoint. It's just proving things that have to do with positive statements in mathematics is often easier than trying to prove things involving negative statements. So that's why we use this formulation of condition 3, that if they intersect at all, then they're exactly the same. All right, so anyway, back to work. I'm going to try and show that if these two cosets, these two left cosets, share X, they have to be exactly the same. Now, the way I'm going to do this is a little bit roundabout. Rather than trying to show directly that these are exactly the same set, which I could do that if I wanted to, I'm instead going to try and take a little bit more efficient route conceptually. That is, I'm going to show that GH is the same coset, exactly the same set as XH, the left coset containing X, and then that's also the same as G'(H). So here's how it's going to go. We're going to start by proving this equality, and then the exact same reasoning will prove this equality. And well, if these two sets are equal, and these two sets are equal, then that means that this set and this set have to be equal. All right, so to show that GH is equal to XH, first let's establish what it means for X to belong to GH, because that's what we're assuming. So since X by assumption belongs to the coset GH, this means there exists H in the subgroup H such that GH is equal to X. That is, X can be written as G times some element of our subgroup. All right, so to show this set equality, let's assume, so we're going to show GH is a subset of XH. Not necessarily a subgroup, because cosets don't have to be subgroups, just subset. Assume Y belongs to GH. All right, then that means there is some, and I'm going to use a different letter here, there's a K belonging to H such that Y is equal to GK. Now, one thing I can do, because I want to show that Y belongs to XH, so I want to write Y as a multiple of X times some element of our subgroup. Now, one thing that might be useful would be to get rid of this G and express it in terms of H. And this equation here gives me a nice tool for doing that. Because GH is equal to X, I can also say, by multiplying the right side of each of these group elements by H inverse, so multiplying on each side of the equation by H inverse on the right, that G is equal to X H inverse. And that's very nice, because now I can say I can say that y is equal to g times k, but that's also equal to, well, g is equal to x times h inverse. So that's x h inverse times k. So that's x times h inverse k. And I know that h inverse is in h, since h is in h. Sorry, I wish there were a better way of saying lowercase h and uppercase h. Maybe I should say h. And then h. So h inverse is in there, and k is in h by our assumption. So h inverse k also belongs to h, because h is a subgroup. It's got to be closed under the group operation. So since h inverse k belongs to the subgroup h, this means, since I've expressed y as x times an element of h, in fact, let's just highlight that here, and y equals x times h inverse k, this means y belongs to xh. Yes. So now we know that at least the coset GH is a subset of the coset XH, and that's 1/2 of what we wanted to show. So now we need to show the other direction, that XH is a subset of GH. So let's assume that Y belongs to XH now. So that means there is some, and I'll pick a different letter again, let's say L belonging to H, such that Y is equal to X times L. All right, now what are we going to do here? We want to show that Y belongs to the coset GH. But now again, I'm going to use the same thinking strategy here. I have Y in terms of X. I would like to get it in terms of G. And I have a nice relationship here between X and G. X is the same thing as GH. Well, that's great. That means I can say, since Y is equal to XL and X is equal to GH, we have Y is equal to GHL. And I can rewrite that as G times HL. And then since H and L both belong to H, and H is a subgroup, the product HL also belongs to H. And since we now have Y is equal to, let me just write this down here. Okay, that feels a little bit better. So Y is equal to G times HL. HL belongs to H. So we have Y belongs to GH. Great. So that means XH is a subset of GH. Subset, not subgroup. There we go. So we've shown that GH and XH are subgroups, sorry, not subgroups, subsets of each other. Therefore, GH is equal to XH. And by the exact same reasoning, because I just said X is something that belongs to both GH and G prime H, I could say by the same reasoning we can also say G prime H is equal to XH. So by transitivity of set equality, GH is equal to G prime H. And so those are exactly the same set. And we figured that out just by knowing that the two share an element X. So now, let's just zoom out for a second here. So now we know that the left cosets, or the right cosets by the same reasoning, the left cosets of a subgroup partition the entire group into disjoint subsets. But let's illustrate that with an example. Again, I'm going to pull in my Cayley table for D4, because I feel like that's a good example. Not commutative, nothing particularly special about it. So let's drop that in. And let's pick a subgroup. Again, let's use our subgroup, I think it was K, which was the identity, and I think we're using H. So let's see if we can come up with the left cosets of K, all of them. Well, first of all, there's R0K, which is really just the subgroup K, because that's the identity times anything in K. So this left coset is going to contain R0 times R0 and R0 times H. That is R0 times any element of K. That's just R0 H. As I said, that's the same thing as the subgroup K. So if I want a different left coset, I'd probably better pick an element not in my subgroup. So let's pick R90. I think that might produce a different left coset. So that's going to give me R90, R0. That's one element of the coset. And then the other one's going to be R90 times the other element of my subgroup, H. And then I know that the first product is just R90. And the second one is going to be R90 times H. Looking at my table, that gives me D prime. Okay, what about R180K? I think that'll give me a different one still. So that's going to give me R180. Sorry, my pen's skipping a lot. When the video gets long, I get punished by having my pen strokes not quite match what I'm doing. So I think that left coset's going to be R180. And then R180 times H is V. And then finally, R270 times K, that's going to be R270, 270 times R0. And then R270 times, I keep doing 220 for some reason, times H, that is R270. And then R270 times H is just plain D. So in this case, the left cosets partition D4 into this partition, R0H, R90D, D prime, R180V, and then R270D. And those account for all 8 elements of the group, and every element is there exactly once. That is, all these subsets are disjoint from one another. I could have also done like H times K, or V times K, or D prime times K, but I would have gotten one of these 4 cosets. And by the way, the partitioning is entirely dependent on which subgroup we choose. If we chosen a different subgroup like R0, R180, or R0V, we would have gotten a totally different partition here, different subsets. So anyway, that's an example that illustrates how the left cosets partition a group.